Have you ever peered into the invisible world of molecules and wondered, why do some chemical reactions burst into life in an instant while others seem to crawl agonizingly slow?
Yeah, it's a great question.
Or perhaps how just a tiny tweak to a molecule structure, just shifting a few atoms, can completely flip how it behaves.
Uh-huh. It really is like a hidden language dictating everything.
It's like a secret language that dictates how the world around us changes.
And today we're diving deep into precisely that secret language. We're pulling back the curtain on the fundamental principles that govern molecular behavior.
Okay.
And we're drawing insights from a really foundational text in chemistry, advanced organic chemistry, Part A, structure and mechanisms, 5th ed.
The classic.
Exactly. Specifically, we'll be exploring its profound chapter on structural effects on stability and reactivity.
Okay, so our mission for you, the curious learner, is to unpack these core concepts, right?
Yeah.
The intricate structures, the clever reaction mechanisms.
And those crucial experimental examples, too.
Yeah, the examples that empower chemists to predict and, maybe more importantly, control chemical behavior.
That control is key.
Think of this as your personal shortcut to truly understanding the why behind the reactions you see every day. I mean, from cooking to manufacturing, it's everywhere.
And we're going to try and define all the key technical terms in a way that, truly makes sense.
Good.
Ensuring you're never lost in the jargon. And we'll highlight the astonishing practical applications that emerge from these principles.
Right, how it shapes things.
Exactly. How they shape everything from designing new drugs to synthesizing advanced materials.
Okay, let's unpack this fascinating world where, quite literally, structure dictates function.
The energy landscape of reactions. Thermodynamics and kinetics.
So let's begin our journey with a concept that seems simple, but has really deep implications. Chemical stability.
Right.
When we talk about a molecule being stable in chemistry, we're not just talking about whether it sits nicely on a shelf for years, are we? What does that really mean?
That's a crucial distinction, yeah. In chemistry, stability isn't really about permanence in that everyday sense. It's fundamentally defined by thermodynamics.
Okay, thermodynamics.
Imagine a vast, undulating landscape, sort of like hills and valleys. The valleys represent stable molecules or maybe fleeting intermediates, while the peaks, the high points, represent the high-energy, unstable transition states.
I've got barriers.
Exactly, the barriers that molecules must cross to transform. So when we talk about free energy change, or AG, for a reaction, we're essentially measuring the elevation difference between where you start, the reactants, and where you end up, the products, on this energy landscape.
Okay.
This, she sets the ultimate thermodynamic limit for how far a reaction can possibly go. If the products are downhill, lower in energy than the reactant.
Yet it wants to go.
Exactly. The reaction is thermodynamically favorable, and it wants to proceed.
And I often hear about enthalpy of formation, or H degrees half. Is that just another way to talk about a molecule stability, or is it different?
It's related, definitely, but with a critical nuance. HF is the energy change when a compound is assembled from its basic elemental building blocks under standard conditions.
Like carbon and hydrogen from methane.
Precisely. Forming methane from solid carbon and gaseous hydrogen. However, a significant limitation is that you can't directly compare H degrees values for compounds made of completely different elements.
Okay.
Like methane versus hydrogen fluoride. Their starting points, their constituent elements, are entirely different.
Right.
So comparing their H degree values doesn't really tell you much about their relative intrinsic stability as molecules.
That's like comparing apples and oranges, kind of.
Exactly. It's like comparing the cost of building a wooden house to a brick house without accounting for the vastly different raw material costs.
Yeah.
It doesn't give you a fair comparison of the structures themselves.
That makes perfect sense. So if H degrees isn't always the best for direct comparison, how do chemists get a more intuitive sense of intrinsic stability, especially for individual chemical bonds within a molecule?
That's where bond energies become incredibly powerful.
Okay, bond energies.
Bond energy is simply the amount of energy required to cleanly break a specific bond, usually homolytically.
Homolytically. What's that mean again?
It just means each atom gets one electron when the bond breaks, a clean split.
Got it.
And this offers a much more comparative measure. For example, if you look at how much energy it takes to break an XH bond as you move across the second row of the periodic table, from carbon to nitrogen, oxygen, and fluorine, you see a very clear and important trend. The energy increases significantly.
So it gets harder to break.
Exactly. a CH bond is weaker than an NH bond, which is weaker than an OH bond, which in turn is weaker than an HF bond.
Wow, okay.
This directly shows the increasing strength and stability of these bonds as the electronegativity of that X atom increases.
That's fascinating. So we can quantify the strength of individual bonds?
Yeah.
What about the overall stability of larger organic molecules, like simple hydrocarbons? Are there general rules for how their structure affects their stability?
Yes, absolutely. For hydrocarbons, two general principles sort of stand out as major stabilizing effects.
Okay.
First, branching in alkanes.
Branching, like more side chains.
Yeah, exactly. And second, double bond substitution in alkenes.
Okay, so more groups attached to the double bond.
Right. This means that an alkane with a more branched carbon skeleton, like isobutane compared to N-butane, it tends to be more stable. And for alkanes, the more alkyl groups attached directly to the carbons of the double bond, the more stable the alkane generally is.
So more alkyl groups always mean more stability. Is that like an unbreakable rule?
Generally, but not always. There's a crucial exception, like you hinted. While it's a general trend, if that branching or substitution leads to significant steric crowding.
Atoms bumping into each other.
Exactly. Atoms getting too close and bumping into each other, causing what we call van der Waals repulsions. That can actually destabilize the molecule.
Okay, so crowding is bad.
Crowding can be bad, yeah. But typically, increased substitution around a double bond leads to greater stability. And you can see this dramatically when you compare HDF degree values for different C6H12 alkenes.
Different isomers?
Right, different isomers of hexene. There's a spread of nearly 7 kilocalories per mole in stability just among these isomers.
That's quite a bit.
It is. For instance, one hexene with its double bond at the end is less stable than, say, 2-cis-3 dimethyl-2-butene, which has the double bond surrounded by 4 methyl groups.
Right, much more substituted.
And that 7 kilocoulomb difference is a significant impact on stability, all just because of how the atoms are arranged.
Yeah.
Structure really matters. 1.2, calculating energies. Tools for prediction.
So we understand what stability is and some general trends. But how do chemists actually calculate these energies? What are the tools they use to, predict stability and reactivity?
Well, one of the most fundamental tools, especially for understanding chemical reactivity when bonds are forming and breaking, is the concept of bond dissociation energies. BDEs. And again, we're talking about homolytic bond dissociation here. The bond splits, one electron to each atom.
Right, the clean split.
Exactly. And looking at VDE data reveals some incredibly important trends. For instance, carbon bonds are considerably stronger than other homonuclear second-row bonds.
What does homonuclear mean again?
Just means bonds between two atoms of the same element.
Okay.
So CC bonds are stronger than, say, O bonds in peroxides or NN bonds.
Ah, interesting.
The dihalogens also show a fascinating, somewhat irregular trend in strength as you go down the group. F2 is weaker than Cl2, then goes down again for Br2 and I2.
Ah, weird.
It is a bit weird. And when we consider bonds to hydrogen, the strength increases from NH to CH, then OH, and finally FH, which is the strongest of that series.
That's incredibly precise. But does the BDE for a particular type of bond, say a CH bond, stay the same no matter what molecule it's in? Or does its environment matter?
Oh, it absolutely does not remain constant. The environment matters hugely. The BDE is significantly affected by the immediate molecular surroundings. Think about CH bonds. The energy required to break a CH bond in simple methane is different from a CH bond in ethane, or a CH bond attached to a tertiary carbon in isobutane. The values can range quite a bit.
Wow.
And the differences are even more pronounced when you compare CH bonds on carbons with different hybridization, like sp3, sp2, or sp carbons.
Right, the orbital type.
Exactly. Similarly, a carbon-carbon bond between two sp2 carbons, like in 1,4-sp-butadiene, is considerably stronger than one between two sp3 carbons.
Okay.
So when you're approximating the overall enthalpy change for a reaction by summing BDEs.
Adding up bonds broken and formed.
Yeah, bonds formed minus bonds broken, essentially. It's critical to select the most appropriate BDE value for the specific bond that's actually breaking or forming in that particular molecule. You can't just grab a generic value.
So, knowing these BDEs, we can essentially add up the energy released when bonds form and subtract the energy needed to break bonds to get an approximate H for a reaction. Can you give us an example of how that helps us predict reactivity?
Sure. Consider the halogenation of ethane. That's adding a halogen like fluorine or chlorine to ethane.
Okay.
If you look at the reaction where a CH bond in ethane breaks and new CX and HX bonds form, where X is the halogen, the H changes dramatically depending on which halogen you use.
How so?
For fluorine, the reaction is very exothermic. Lots of energy released.
Right, fluorine's reactive.
Extremely. As you move down the halogen group to chlorine, then bromine, and finally iodine, the reaction becomes progressively less exothermic.
Okay.
Eventually, it actually becomes endothermic for iodine. It requires energy input.
Wow, so it won't really happen easily.
Exactly. And this perfectly illustrates how the strengths of the newly formed CX and HX bonds, reflected in their BDEs, dictate the overall energy release or requirement for the reaction. It gives you a clear picture of relative reactivity, F2Cl2Br2I2.
That neatly connects bond strength to overall reaction energy. Now, beyond individual bonds, I recall hearing about electronegativity and how it influences bond strength. How does that fit into this picture?
That brings us to the pioneering work of Linus Pauling, a giant in chemistry.
Definitely.
He recognized a profound connection. The difference in electronegativity between two bonded atoms directly contributes to the bond's strength.
Yeah.
He even proposed empirical relationships, basically formulas, showing that there's an electrostatic increment to bond strength. It's like an extra bit of glue holding the atoms together, and it grows with the difference in electronegativity.
So it's not just sharing electrons, there's an attraction too.
Precisely. Beyond just sharing electrons in the covalent bond, there's this additional electrostatic glue holding things together more tightly if the atoms have different poles on the electrons. It was a remarkable insight.
And has that original idea stood the test of time, or have chemists, refined it?
Oh, it has been refined, certainly. But Pauling's core idea remains incredibly influential. More recently, researchers like Zavintzis re-examined Pauling's equation and found it still aligned remarkably well with modern thermochemical data.
That's impressive.
It really is. And this allowed them to assign electronegativity and, critically, a stabilization energy, SE, to important reaction intermediates, especially radicals.
Radicals, the ones with unpaired electrons.
Exactly. And this revealed a crucial radical stabilization order. It turns out allyl and benzyl radicals, those next to double bonds or benzene rings, are far more stable than, say, tertiary or secondary alkyl radicals, which are themselves more stable than primary alkyl radicals. This quantitative approach helps chemists understand why certain radicals hang around longer or form more easily than others.
That sounds like electrons are constantly trying to find a balance, like slowing to where they're most comfortable. Is there a core concept that describes this inherent electron flow?
You're hitting on the concept of electronegativity equalization. It's a really neat idea. Yeah. This idea, now firmly supported by quantum calculations like density functional theory, DFT, basically says that when atoms bond, electron density flows from the less electronegative atom to the more electronegative one until the effective electronegativities of both atoms in the bond become equal.
Like water finding its level.
Exactly like that. At this point, there's no longer a net pull on the electrons. And this fundamental principle helps explain observed trends in bond strength and reactivity.
Like what?
For instance, when an alkyl group is attached to a highly electronegative substituent like a halogen or oxygen, the bond strength often appears to increase as you go from a methyl group to a primary, secondary, and then tertiary alkyl group.
Okay.
But, intriguingly, this trend reverses for organometallics and boranes. It flips, which showcases the real subtlety of how electrons move around.
So we can calculate energies for individual bonds using BDEs, but can we predict the enthalpy for an entire molecule just by summing up contributions from its smaller pieces, like building with chemical Legos?
Exactly. That's the perfect analogy. This leads us to transferable group equivalence, and the most famous approach here is Benson's additivity scheme.
Benson's scheme?
Yeah. The brilliant insight is that specific molecular groups, like a CH3 group, a CH2 group, or a C atom in various environments, tend to have very consistent energy contributions, pretty much regardless of the larger molecule they're part of.
So they're like standard building blocks.
Precisely. So you can calculate the enthalpy of formation of a complex molecule like isoctane, which is in gasoline, by simply adding up the established energy contributions from all its constituent, CH3, CH2, CH, and C groups.
Wow.
This was a game changer, because it offered a relatively simple way to predict molecular energies without needing full-blown complex calculations, which used to take ages. It dramatically accelerated the ability to estimate thermodynamic stability for new or even hypothetical molecules.
That seems incredibly powerful for predicting energies, but I imagine there's some situations where it might not be quite right.
Right.
Like limitations. Yeah.
You're astute to pick up on that. Yes, there are limitations. The main one for Benson's scheme is that it basically assumes molecules are strain-free.
Strain-free.
Yeah, it doesn't automatically account for long-range non-bonded interactions or conformational strain, like the subtle energy penalty you get from gauche interactions in alkanes where groups are close but not bonded.
Ah, okay. That's steric crowding again.
Kind of, yeah. For those, you need to add specific correction terms to the Benson sum.
Okay.
Another clever approach, pioneered by Leroy, involves comparing the sum of standard bond energies to the actual measured atomization. Enthalpy is the energy to break a molecule into all its individual atoms.
What's that tell you?
The difference reveals any extra stabilization effects, things the simple sum doesn't capture. For example, this method beautifully reveals the extra stabilization energy that comes from conjugation in butadiene, that alternating double single bond system. Or it can pinpoint the fascinating anomeric effect that adds extra stability to molecules like dimethoxymethane. These insights allow chemists to identify where unique electronic interactions are providing unexpected stability beyond just simple bonds.
So we have these powerful empirical schemes like Benson's. What about the cutting edge of energy calculations? What are the most accurate computational methods chemists use today?
For the highest accuracy in predicting AHF and understanding molecular properties, computational chemists turn to ab initio methods and density functional theory, or DFT.
Ab initio and DFT, heard of those?
Yeah, they're based on fundamental quantum mechanics and have become incredibly sophisticated and powerful. High-accuracy methods can compute AHF values that are remarkably close to experimental measurements, sometimes within 1 kilocalorie or even better.
Wow.
And to achieve even greater precision, maybe within a tiny fraction of a kilocalorie per mole, chemists employ something called isodesmic reactions. It sounds fancy, but the idea is clever. These are hypothetical reactions you design computationally so that the types of chemical bonds broken and formed are conserved on both sides of the equation.
Why do that?
Because it allows computational errors, which often affect similar bond types, similarly, to cancel out very effectively. This strategy leads to extremely accurate predictions of AH.
So what does this all mean? We can calculate stability with incredible precision using Benson or DFT or isodesmic reactions. Yep. But does that tell us anything about how fast a reaction happens?
The million-dollar question. Crucially, no. The enthalpy change or even the free energy change of a reaction gives no information whatsoever about its rate.
No.
None directly. The speed of a reaction is determined not by the ultimate energy difference between reactants and products, but by the energy of the transition state. More precisely, the free energy of activation, that double dagger, means activation.
Okay.
It's the height of the energy barrier relative to the starting materials, not the depth of the valley at the end, that dictates speed.
But how can we know anything about these transition states if they're so fleeting? You said they're unstable peaks. You can't just, put them under a microscope, can you?
Exactly.
Yeah.
That's the challenge. Since transition states are inherently transitory, existing for maybe only a fraction of a picosecond.
Wow, that's fast.
Incredibly fast.
Yeah.
We have no physical means to isolate them or directly determine their structure experimentally. However, their energy can be powerfully inferred from reaction kinetics studying the rates.
Okay, so rates tell us about the barrier height.
Exactly. And this is where modern computational methods, particularly molecular orbital MO theory and DFT calculations, become absolutely invaluable. These methods allow us to theoretically calculate transition structures, which we often abbreviate as TS.
Calculate the peak.
Calculate the structure and energy at the peak, yeah. And we can map out the minimum energy pathway, also known as the intrinsic reaction coordinate, or IRC, that a reaction follows from reactants over the TS to products.
So if a transition state isn't a stable molecule, what exactly is it on that energy landscape you described earlier, that hill and valley picture?
It's very specific. It's a saddle point on the potential energy surface.
A saddle point? Like on a horse?
Kind of.
Yeah.
Think of being on the absolute highest point of a mountain pass connecting two valleys.
Hmm.
You're at a minimum in energy if you try to go sideways off the path.
Right.
But you're at a maximum in energy along the path you're traveling, from one valley to the other.
Ah, okay. Minimum in all directions except one.
Precisely. A TS represents the highest energy point along the reaction coordinate for a particular step. And what's truly remarkable is that computationally, a transition structure possesses a unique mathematical signature.
What's that?
It has a single imaginary vibrational frequency.
Imaginary?
Yeah.
Like, it's not real.
It's not a real vibration you could measure with spectroscopy, no. It's a mathematical result from the calculation. But this imaginary frequency corresponds precisely to the direction of motion, the bond breaking and bond forming that leads the molecule over the saddle point, from reactants towards products.
So it's the proof you found the right spot.
It's the computational proof that you found that exact fleeting moment of transformation, the peak of the barrier.
The world of kinetics.
That's a powerful idea, inferring fleeting structures and energies through calculation and kinetics. Now let's shift gears properly from understanding stability, which is thermodynamics, to quantifying reactivity, which you mentioned is the domain of chemical kinetics.
All right, kinetics is all about rates.
What are the fundamental principles at play here that determine how fast a reaction actually goes?
Chemical kinetics is indeed how we rigorously quantify reactivity. And the free energy of activation is the single most important parameter.
That barrier height again.
Exactly. It directly dictates the rate constant, Kr, for a reaction. A large daily means there's a high energy barrier to overcome, and thus a slow reaction, a small eta, a fast reaction.
Okay.
The theoretical framework we use to understand this is called transition state theory. It proposes that reactions proceed through an activated complex.
Activated complex, is that the same as a transition state?
Yeah, pretty much another name for the transition state. This complex is thought to be in a very rapid, fleeting equilibrium with the reactants, and then it quickly converts to products. It's the species right at the top of the energy barrier.
So AJ gives us the overall energy barrier, but just like G can be broken down into enthalpy and entropy, isn't data also composed of different factors?
It absolutely is. And understanding these components gives us deeper insight. D has two key parts: the enthalpy of activation and the entropy of activation.
Okay, activation enthalpy and activation entropy.
Right. H reflects the energy required to reorganize bonds, stretching them, bending them within the molecule as it strains and contorts to reach that high-energy transition state structure.
The energy cost of distortion.
Pretty much, yeah. H, on the other hand, is a measure of the change in molecular ordering or freedom as the system moves from reactants to the transition state.
Ordering, like how messy it is.
Exactly. It includes changes in how molecules can move around, translation, vibrate, and rotate. It tells you how much more organized or disorganized the system becomes just to get over that energy hump.
Can you give us some vivid examples of how ASIA plays out in real reactions? What might cause a positive or a negative ASIA?
Certainly, a negative base means the system becomes more ordered and loses freedom when forming the transition state. A classic illustration is the dimerization of cyclopentadiene.
Two molecules coming together.
Right. This reaction has a significantly negative S, around -34 entropy units. Why? Because two independent, freely moving cyclopentadiene molecules must collide and come together to form a single, highly organized cyclic transition state.
They lose freedom.
They lose a tremendous amount of translational and rotational freedom in the process. They go from two things flying around to one thing forming a specific shape. That leads to a big decrease in entropy, a negative S.
And a positive S would be the opposite? More freedom.
Precisely. A positive S indicates an increase in molecular freedom, typically when a single molecule breaks apart into multiple fragments. For instance, the thermal decomposition of 11,1-azobutane. This molecule splits into 3 smaller fragments when heated. The S is positive, about +19e.
Makes sense. One thing becomes 3.
You're gaining significant translational degrees of freedom as the fragments separate and fly off independently. More disorder, positive S's.
And how do solvents fit into this? I imagine reorganizing solvent molecules around a forming charge would have a big impact on entropy, wouldn't it?
You're getting on a critical point. In solution, the organization of solvent molecules around the reacting species is immensely important and often dominates the entropy change.
Really?
Yeah. Take the solvolysis of T-butyl chloride. It's an SN1 reaction. Its rate-determining step involves the unimolecular ionization of the carbon-chlorine bond to form a T-butyl carbocation and a chloride anion.
One molecule becomes 2 ions.
Right. So you might intuitively think forming 2 particles from one would lead to a positive Cromall disorder.
Seems logical.
But the observed dizzy is actually negative, about -6.6 Hammond.
Negative. Why?
Because the highly charged and polar transition state, where the CCl bond is breaking and charges are developing, requires a much greater ordering of the surrounding polar solvent molecules like water or alcohol around it. The solvent molecules have to arrange themselves just so to stabilize those developing charges. This solvation effect, this ordering of solvent, decreases the overall entropy of the system more than the creation of two particles increases it.
So the solvent tidying itself up outweighs the molecule splitting apart.
In this case, yes. Reactions that generate charged species in solution usually exhibit negative entropies of activation for precisely this reason. The solvent organization is key.
These energy diagrams truly help visualize the process. How do chemists typically use them to depict reaction pathways, showing these peaks and valleys?
We use reaction energy profiles, sometimes called reaction coordinate diagrams. Imagine a graph where the vertical axis is energy, usually free energy, G, and the horizontal axis is the reaction coordinate.
The reaction coordinate, that's like the progress of the reaction.
Exactly. It represents the structural changes along the lowest energy path from reactants to products. These diagrams clearly differentiate between intermediates and transition states.
Right, valleys and peaks.
Precisely. An intermediate sits in an energy minimum, a valley, on the profile. It has a finite, albeit sometimes very short, lifetime. The deeper that energy valley, the longer the intermediate's lifetime, generally. A transition state, on the other hand, is an energy maximum, a peak, along the reaction coordinate. It has only that fleeting picosecond existence.
And is there a fundamental rule about these paths?
Yes, a very important one. The principle of microscopic reversibility. It states that the exact same pathway through the same intermediates and transition states is followed in both the forward and reverse directions of a reaction, just in opposite sequence. The lowest energy path is the same both ways.
So far, we've mostly talked about these one-dimensional energy diagrams just following one path, but many reactions involve changes in multiple bonds simultaneously, right? How do chemists represent that added complexity?
That's a great point. For reactions involving changes in two different bonds, we can move to two-dimensional energy diagrams, sometimes called Moore-O'Farrell-Jenks plots.
Okay, 2 dimensions.
Imagine a square plot where one axis represents the breaking of one bond and the other axis represents the forming of another bond. These diagrams can beautifully depict different mechanistic pathways. For instance, a dissociative path, where one bond breaks completely before a new one forms, might follow along two edges of the square.
Got it.
An associative path, where a new bond starts forming before the old one breaks significantly, might follow the other two edges. And a concerted path, where bond breaking and bond forming happen more or less simultaneously.
Goes diagonally.
Exactly. It follows a diagonal path across the plot. The actual path traces the lowest energy route on this 2D surface.
Clever.
And for even greater complexity, like reactions involving changes at 3 bonds, chemists sometimes use conceptual 3-dimensional reaction cubes. These aren't usually drawn in full detail, but they serve as a framework to summarize intricate mechanistic conclusions, helping chemists visualize and discuss really complex transformations involving multiple simultaneous changes.
Unpacking reaction rates,
Right.
mechanisms in control, 2.1 kinetic expressions, deciphering the rate law.
That's a lot of information we can infer just from thinking about energy landscapes and pathways. Now, how do experimental chemists gather the actual data in the lab to build these mechanisms and understand reaction rates? How do they measure how fast things are going?
The primary way is through collecting experimental kinetic data. Basically, you meticulously monitor how reactant concentrations decrease or product concentrations increase over time.
How do they monitor that?
There are lots of techniques. Common methods include spectroscopy, like UVVs or NMR, which tracks changes in light absorption or magnetic resonance signals as molecules change.
Okay.
If ions or acids bases are involved, you might use pH measurements or conductance measurements.
Yeah.
For reactions involving chiral molecules, polarimetry can track changes in optical rotation.
So the goal is to get a quantitative relationship, right? Something specific you can write down.
Exactly. The ultimate goal is to establish a quantitative mathematical relationship, an equation between the concentrations of all reactants and catalysts and the observed reaction rate. This equation is called a rate law or rate expression.
The rate law.
Yes. This algebraic formula contains one or more rate constants, which depend on temperature but not concentration. In concentration terms for all species involved, up to and including the rate-determining step, the slowest step in the mechanism.
And the exponents on those concentrations matter.
Hugely. Each concentration term has an exponent, which defines the kinetic order with respect to that specific component. If the exponent is 1, it's first order in that component. If it's 2, it's second order, and so on.
Okay.
And the sum of all these exponents gives the overall kinetic order of the reaction, For example, a reaction whose rate is directly proportional to the concentration of a single reactant is first order overall.
And how do you find those orders experimentally?
You vary the concentrations and see how the rate changes. Or you can plot the data in specific ways. For instance, plotting the logarithm of concentration versus time gives a straight line for first-order reactions. Plotting one concentration versus time gives a straight line for simple second-order reactions.
Many organic reactions involve multiple steps and those fleeting intermediates we talked about. How do chemists simplify these complex mechanisms to derive a usable rate law that actually reflects what's happening and controlling the speed?
Yeah, mechanisms can get complicated quickly.
Yeah.
Chemists employ two very powerful conceptual tools, two approximations, to handle this.
Okay.
The first is the pre-equilibrium approximation. This is used when a fast reversible step happens before the slow rate-determining step.
Fast equilibrium first.
Right. In this scenario, the concentration of any intermediate formed in that fast equilibrium can be expressed using an equilibrium constant, Keck, which relates it back to the reacting concentrations. This lets you substitute and simplify the overall rate law, getting rid of the intermediate's concentration term.
Okay, that helps. What's the other one?
The other is the steady-state approximation. This one is incredibly useful for those highly reactive, unstable intermediates whose concentrations remain very low throughout the reaction because they react almost as soon as they're formed.
Low concentration, short lifetime.
Exactly. The core idea of the steady-state approximation is that the rate at which such an intermediate is formed is approximately equal to the rate at which it is consumed. It doesn't build up.
Okay.
By setting these rates equal, rate of formation, rate of destruction, you can solve algebraically for the intermediate's tiny, steady concentration, and then substitute that expression into the rate law for the overall reaction.
So both methods help get rid of intermediate concentrations.
Essentially, yes. They allow you to express the overall rate in terms of measurable reactant and catalyst concentrations. And perhaps most importantly, applying these approximations correctly often helps pinpoint which step in a multi-step mechanism is the rate-determining step.
The bottleneck?
Exactly. It tells you which molecular transformation is the slowest part, the bottleneck that controls the overall speed of the reaction.
Can you walk us through a real-world example to illustrate how these kinetic studies help chemists actually figure out that rate-determining step?
Sure. A great example is the base-catalyzed condensation of benzaldehyde and acetophenone. It's a type of aldol condensation, very common in organic synthesis.
Okay.
Chemists proposed a plausible, reversible mechanism. First, the base takes a proton off acetophenone to form an enolate ion.
Right, the carbanion.
Then this enolate attacks the benzaldehyde carbonyl carbon in a nucleophilic addition. This is followed by a fast proton transfer and finally a dehydration step where water is lost to form the final conjugated product.
Okay, several steps.
Now the kinetic question is, which step is slowest? If that initial deprotonation were the rate-controlling step,
The first step.
the rate expression would only depend on the concentrations of acetophenone and the base.
Yeah.
Surprisingly, it would not depend on the concentration of benzaldehyde because benzaldehyde isn't involved until the second step.
Interesting.
But if the second step, the addition of the enolate to benzaldehyde, were the bottleneck, the rate expression derived using the pre-equilibrium approximation for the first step would be third order overall. It would depend on acetophenone, the base, and benzaldehyde.
Okay, third order.
Intriguingly, the same third-order expression would also result if the final dehydration step were rate-controlling, assuming all the preceding steps are fast equilibria.
Uh-oh. So how do you distinguish between those last two possibilities if they give the same predicted rate law?
This is where the truly clever experimental work comes in. It's not just about measuring the initial rate.
What did they do?
Initial studies of this specific condensation revealed it was, in fact, third order. So that immediately eliminated the first possibility deprotonation couldn't be the slow step.
Okay, ruled one out.
Right. To distinguish between the addition step, step 2, and the dehydration step, step 4, being rate limiting, chemists had to do more. They actually synthesized the intermediate molecule formed after the addition step by a completely different route.
Made the intermediate separately.
Exactly. And then they studied its reactivity separately under the reaction conditions. These studies show that the subsequent dehydration of this intermediate was about 4 times faster than the reverse reaction, going back to enolate and benzaldehyde. Crucially, these later steps were also much, much faster than the overall condensation reaction they were originally studying.
So the later steps weren't the bottleneck.
Precisely. This independent experimental evidence confirmed that the second step, the nucleophilic addition of the enolate to benzaldehyde, is indeed the rate-controlling step. It's like being a detective, meticulously gathering clues and eliminating suspects until only one solution fits all the evidence.
That's a perfect illustration of how kinetic data helps narrow down possibilities. So, kinetic results can exclude mechanisms, but can they ever definitively prove one specific mechanism is the only possibility?
That's a very important philosophical point in chemistry. Generally, no, kinetic data can't definitively prove a mechanism in isolation, because kinetic results are incredibly powerful for excluding mechanisms that simply don't fit the observed rate law. But as we just saw, sometimes different plausible mechanisms can lead to kinetically equivalent read expressions. You can't distinguish between them based solely on kinetics.
Okay.
Furthermore, while kinetic data tells you the composition of the activated complex, that is, what atoms and molecules are involved in the transition state for the rate-determining step, it provides no direct information about its precise 3D structure or how the bonds are changing. That structure is often inferred from related chemical experience, like how similar reactions behave, or, as we discussed, from sophisticated computational studies that model the transition state. Kinetics gives you the who, but not necessarily the how. 2.2 Kinetic versus thermodynamic control. Which product wins?
So reactions follow certain paths, and their rates depend on the energy barriers. But what happens when a reaction has a choice, when it can lead to multiple different products? How does a chemist predict which one will actually form, or maybe more importantly, how to force it to form the desired one?
This brings us to an absolutely critical distinction in organic synthesis. Thermodynamic control versus kinetic control. It's all about managing competition.
Thermodynamic versus kinetic control. Okay.
Imagine a reaction starting from some reactant R that can produce two different products. Let's call them A and B.
R goes to A or B.
Right. When a reaction is under thermodynamic control, the product composition is governed by the relative equilibrium stability of the competing products, A and B.
How stable they are at the end.
Exactly. Given enough time and, crucially, reversibility, meaning A and B can potentially convert back to R or even interconvert between A and B, the most stable product, the one with the lowest overall free energy, will eventually dominate. The system settles into its lowest energy state.
Okay, that's thermodynamic control. What's kinetic?
If the reaction is under kinetic control, the product composition is dictated instead by the competing rates of formation of A and B.
How fast they form.
Precisely. Here, the fastest formed product, the one that has the lowest activation energy barrier to its transition state, will be the major product initially, even if it's actually less stable overall than the other possible product. Speed wins over stability.
Can you give us an analogy to illustrate this, maybe visually on one of those energy landscapes?
Absolutely. Imagine you're standing on a hill, the reactant, and there are two paths down leading to two different valleys, the products.
Okay.
One path is quite steep but short, leading quickly to a shallow, less stable valley, product A, the kinetic product. The other path requires climbing over a higher initial ridge, higher activation energy. It's a slower path, but it leads down into a very deep, stable valley. Product B, the thermodynamic product.
Okay, I can see that. Fast path to a shallow valley, slow path to a deep valley. So what controls which path you take?
It often comes down to the conditions. If you're rushing, maybe the conditions are harsh and the reaction is irreversible. You can't climb back out of the valleys easily.
One-way trip?
You'll likely take the short, steep path just because it's quicker. You end up in the shallower valley. That's kinetic control. You prioritize speed.
Right.
However, if you have plenty of time, and maybe the conditions allow you to easily move between valleys or even back up the hill, the reactions are reversible.
Equilibration.
You'll eventually settle in the deepest, most comfortable valley, product B. That's thermodynamic control. You prioritize ultimate stability.
And how do chemists control this in the lab?
Temperature.
Time.
Exactly, those things.
Yeah.
Lower temperatures or shorter reaction times often favor the kinetic product because there isn't enough thermal energy for many molecules to overcome the higher activation barrier to the thermodynamic product, or maybe not enough time for the system to equilibrate, even if it's reversible. But at higher temperatures, or with longer reaction times, assuming reversibility, the less stable kinetic product might have enough energy to revert back or convert over to the more stable thermodynamic product. The system can then reach true equilibrium, favoring the most stable outcome. Even adding a catalyst can fundamentally shift this, maybe by providing an easier pathway for the kinetic product to convert to the thermodynamic one.
That's an incredibly powerful concept for synthetic chemists. Can you give us a practical example where controlling these conditions is absolutely crucial for getting the right product?
A prime practical application is the formation of enolate anions from unsymmetrical ketones, like, say, 2-methylcyclohexanone.
Okay, a ketone with the different hydrogens next to the carbonyl.
Exactly. This is a vital reaction in organic synthesis, as enolates are key building blocks for making CZ bonds. These unsymmetrical ketones can often form multiple different enolates depending on which alpha hydrogen, the hydrogens on the carbons next to the CO, is removed by the base.
Right, one side might be more crowded than the other.
Precisely. And the conditions you choose dramatically dictate whether you get the kinetic enolate or the thermodynamic enolate.
How does that play out in the lab? What base? What temperature?
Okay, so if you want the kinetic enolate, you typically use a very strong sterically hindered base. The classic example is lithium disisopropylamide, LDA.
LDA, big and bulky.
Big and bulky, right.
Yeah.
And you do this at low temperature, often -78 degrees C, in a non-hydrogen bonding aprotic solvent like THF. The bulky LDA preferentially grabs the less sterically hindered proton because it's easier to reach, and it does so quickly and irreversibly at low temp. That gives you the less substituted enolate, the kinetic product.
Okay, LDA, low temp, less substituted enolate. What about the thermodynamic one?
If you want the more stable thermodynamic enolate, which is usually the more substituted one, like a more stable alkene,
Right.
you use different conditions, maybe a weaker base or even just a catalytic amount of base, often in a protic solvent like an alcohol or at higher temperatures. Under these conditions, the proton transfer becomes reversible. The enolates can interconvert.
They can swap protons around.
Exactly. Given enough time, the system will equilibrate, and the equilibrium will favor the formation of the more stable thermodynamic enolate. So simply by changing your choice of base, solvent, and temperature, you can switch from forming one enolate preferentially to forming the completely different one. It's a beautiful example of the exquisite control chemists can exert just by tweaking the environment.
When kinetics and thermodynamics align, or don't,
it's clear that stability, thermodynamics, and reactivity, kinetics, are distinct concepts, but they often seem intertwined. So is there any inherent relationship between a reaction's overall free energy change, how favorable it is, and its activation energy, how fast it is? Do reactions that release a lot of energy generally tend to be faster?
That's a very fundamental question, and the answer is sometimes, but not always. There's no strict universal law that says a highly favorable reaction must be fast or that a less favorable one must be slow. You can have very favorable reactions that are incredibly slow because of a high activation barrier.
Like diamond turning into graphite.
Exactly. Thermodynamically favorable, but kinetically forbidden at room temperature. However, it is very often observed that such relationships do exist, particularly within a series of closely related reactions where the mechanism is similar.
So when they are related, how do chemists conceptualize that connection between a reaction's overall energy profile and the structure of its fleeting transition state? How does the stability difference relate to the barrier?
This is where Hammond's postulate comes in. It's a cornerstone concept, really insightful for understanding reaction mechanisms.
Hammond's postulate?
Yeah. It simply states that if two states along a reaction coordinate, for example, the transition state and the reactants, or the transition state and a product or intermediate, are close in energy, then their structures will also resemble each other.
Closer in energy means closer in structure.
Essentially, yes. So, for a very exothermic reaction step, where the transition state is much lower in energy than the reactants and therefore closer in energy to the reactants, we describe it as an early transition state. Structurally, it looks a lot like the starting materials. The bonds haven't changed much yet.
Okay, early TS for exothermic.
Right. Conversely, for an endothermic step, where the transition state is higher in energy than the reactants and closer in energy to the higher energy products, or intermediate, we call it a late transition state because its structure is more product-like or intermediate-like. The bonds have changed quite a bit, almost reaching the product structure. It's like a blurry photo. The closer in energy 2 points are on the reaction path, the more their structures resemble each other.
How does Hammond's postulate help us understand something as fundamental as electrophilic aromatic substitution? Where certain groups on a benzene ring direct incoming groups to specific positions, ortho, meta, or para, and make the reaction faster or slower.
Electrophilic aromatic substitution is an excellent real-world application, yes. In these reactions, the ultimate product composition, specifically the isomer ratio, how much ortho, meta, or para product you get, is usually kinetically controlled.
So it depends on the rates of formation.
Exactly. Which means the ratio is determined by the relative energies of the respective transition states that lead to those different isomers. Now, in the transition state for this reaction, a positive charge is developing on the benzene ring as the electrophile, the electron-seeking group, attacks.
Okay.
According to Hammond's postulate, since this step is often endothermic, forming the charged intermediate costs energy, the transition state structurally resembles the intermediate that follows it. And that intermediate is the complex, the species, with a full positive charge delocalized around the benzene ring.
So the transition state looks like the sigma complex.
It resembles it, yes. It has significant sigma complex character.
Can you illustrate this with a specific example?
Yeah.
Like, compare methoxybenzene, anisole, to nitrobenzene. It seems counterintuitive that one group activates the ring and directs orthopara, while the other deactivates and directs meta.
Absolutely. It's a perfect illustration. Take methoxybenzene. The oxygen of the methoxy group has lone pairs, making it electron-releasing through resonance. This group can stabilize the positive charge that forms in this complex intermediate by donating its lone pair electrons, particularly when the positive charge develops at the ortho and para positions relative to the methoxy group. You can draw resonance structure showing the positive charge on the oxygen.
Right, stabilizing resonance.
This stabilization lowers the energy of the intermediate, and therefore, by Hammond's postulate, it also lowers the energy of the transition state leading to it. As a result, methoxybenzene reacts significantly faster than plain benzene, and it leads predominantly to ortho and para substitution products.
Okay, activating and orthopara directing. What about nitrobenzene?
Now contrast that with nitrobenzene. The nitro group is strongly electron withdrawing due to both induction and resonance.
Pulls electrons away.
Strongly. It therefore destabilizes the positively charged complex. This destabilization is especially pronounced if the electrophile attacks at the ortho or para positions, because you'd end up with resonance structures where the positive charge is on the carbon directly attached to the electron-withdrawing nitro group, a very unfavorable situation, like charges next to each other.
Okay, that's bad.
Very bad energetically. While the metatransition state is also destabilized relative to benzene, because the nitro group is withdrawing overall, it's significantly less destabilized than the ortho or para pathways, because you avoid that direct unfavorable interaction.
So meta is the least bad option.
Essentially, yes. As a result, nitrobenzene is much less reactive than benzene overall. It's deactivated. And the product that does form is overwhelmingly the meta isomer. This beautifully demonstrates how powerful resonance effects are, often dominating the outcome in these aromatic systems.
So we have these qualitative relationships like Hammond's postulate. Are there any more quantitative equations that try to actually link activation barriers to the overall energy of a reaction?
Yes, there are more quantitative approaches. One important one is the Marcus equation.
Marcus equation.
It's a sophisticated theoretical tool rooted in electron transfer theory initially, but applicable more broadly. It endeavors to mathematically relate the activation barrier of a reaction to its overall reaction-free energy, often involving a term called the reorganization energy.
What's its value?
Its immense potential lies in its ability, in principle, to predict reaction rates based on equilibrium data, which is often easier to obtain experimentally or computationally. It tries to quantify that relationship we discussed. How much faster should a reaction get if it becomes more favorable?
Has it been used successfully?
Yes, for certain types of reactions, it works remarkably well. For example, the Marcus equation has been successfully applied in detailed studies of the aldol condensation reaction, showing strong correlations for both the initial addition step and the subsequent elimination step. It allows chemists to make quantitative predictions about how changes in structure affect the rates of these fundamental reactions.
Finally, we talked about how conformational stability can affect a molecule like chair forms of cyclohexane. But how do these fleeting conformational changes within a reactant affect the overall reaction rate and product outcomes? If a molecule exists in two forms, does the reaction just happen from the more stable one?
This is addressed by the Curtin-Hammett principle. It's a truly counterintuitive but vital concept for understanding reactivity.
Curtin-Hammett. Okay, what's the idea?
The key idea is this. If the energy barrier for a chemical reaction is much greater than the energy barrier for conformational equilibration between different shapes, conformers, of the reactant.
Meaning the shapes interconvert really, really fast compared to the reaction.
Exactly. If the conformers interconvert rapidly, then the ratio of products formed from those different conformers is not controlled by the relative populations or stabilities of the starting conformers themselves.
Wait, it doesn't depend on which conformer is more stable. That seems weird.
It does seem weird, but what it means in practice is that a reaction can preferentially proceed through a minor, less stable conformation of the reactant if that particular, even fleeting conformation provides access to the lowest energy transition state leading to a product.
So the easiest path might start from an unstable shape.
Precisely. It's the energy of the transition states that matters for the product ratio, not the energy of the starting conformers, provided those conformers interconvert quickly. It's a powerful reminder that the most abundant starting material isn't always the one that reacts fastest.
Does this apply elsewhere?
Yes. The principle applies broadly to any situation involving rapid pre-equilibria before a slower reaction step, such as tautomerism, like keto-enol tautomerism as well. It emphasizes again and again. Kinetics is controlled by the relative heights of the transition state barriers.
The power of substituents. Electronic effects on intermediates.
Now, let's really dive into one of the most powerful concepts in organic chemistry. How attaching different groups, different bits of structure, what we call substituents, to a molecule influences how it reacts. It's like giving a molecule a specific personality, right?
Absolutely. Substituents are key controllers. They alter reaction rates primarily by changing the free energy of activation of the rate-determining step.
Lowering or raising that barrier.
Exactly. These effects are broadly categorized. There are electronic effects, which we'll focus on. There are steric effects, just bulk getting in the way. And sometimes structure-specific effects, like strain. But today, let's dig into the incredibly intricate electronic effects.
Okay. What are the different ways these electronic effects actually manifest? How do they talk electronically to the rest of the molecule?
They work in a few fundamental ways. First, through delocalization. This means spreading out electrons.
Like resonance.
Exactly. Resonance, the movement of pi electrons through conjugated systems, is a major type. But also hyperconjugation, that subtle sharing of sigma bond electrons we mentioned for carbocations. Okay. Crucially, delocalization often requires specific orbital alignment things need to line up correctly. We call these stereoelectronic requirements.
Got it. What else?
Second, they operate via polar effects. These are essentially electrostatic interactions.
Charges attracting or repelling.
Pretty much. These arise from permanent bond dipoles due to electronegativity differences, or from charges that are more distant within the molecule interacting through space. Polar effects are sometimes subdivided. Inductive effects are the local electronic changes transmitted through sigma bonds.
Like pulling or pushing electrons through the chain?
Yeah, kind of. And field effects are direct through-space electrostatic interactions between parts of the molecule. The distinction can be blurry sometimes.
Okay. And the last one.
And finally, polarizability effects. This is about how easily the electron cloud of a group can distort or deform in response to a nearby charge or electric field. Bigger, mushier electron clouds are more polarizable. This is particularly important in the gas phase, where there's no solvent to mediate these interactions.
Right. We'll examine these fascinating effects through the lens of 4 crucial reaction intermediates, starting with maybe the most well-known.
Positive charges, surprising stability.
Okay, starting with carbocations. Those species with a positive charge formally on a carbon atom. What fundamentally determines their stability? Why do some seem to vanish instantly while others can actually be observed, at least fleetingly?
Carbocations are indeed highly reactive intermediates, inherently unstable because carbon doesn't like having only 6 electrons in a positive charge. But their stability is dramatically increased by adjacent groups that can donate electron density into their empty orbital.
Filling the void, so to speak.
Exactly. This electronic donation helps to spread out or delocalize that concentrated positive charge, making the whole species less unhappy. And this elegantly explains the observed stability order everyone learns. Tertiary, secondary, primary mesocarbocations.
More alkyl groups, more stable.
Right. A tertiary carbocation surrounded by 3 electron-donating alkyl groups is far more stable than a poor methycation with only hydrogens.
How exactly do these simple alkyl groups, like a methyl or ethyl group, achieve this stabilization? Is it just about pushing electrons through bonds, the inductive effect?
It's a combination of 2 effects, actually. First, yes, inductive effects play a role. Alkyl groups are generally considered to be mildly electron-donating through their sigma bonds, pushing a bit of electron density towards the positively charged carbon.
Okay, little push.
But arguably even more significantly, it's through hyperconjugation.
Hyperconjugation again. How does that work here?
It involves the subtle delocalization of electron density from adjacent CH or even CC sigma bonds into the vacant p orbital of the carbocation center. You can visualize the electrons in those nearby sigma bonds, partially overlapping or sharing themselves with that empty p orbital.
So the sigma electrons help out the empty p orbital.
Exactly. This helps to spread out the positive charge over more atoms, including the hydrogens. And this hyperconjugation is quite powerful. Calculations show it can account for substantial stabilization, maybe up to 75 kilocalories per mole difference between a tertiary butyl cation and a simple methyl cation.
Wow, 75 kilocation is huge. What about more complex structures, like those with double bonds or aromatic rings nearby?
Now you get even more stabilization. Allylic next to CC and benzylic next to a benzene ring, carbocations are exceptionally stabilized, primarily by resonance.
Resonance drawing structures.
Right. The pi system of the adjacent double bond or aromatic ring allows the positive charge to be formally distributed over multiple carbon atoms via those resonance structures you can draw. This charge delocalization dramatically lowers the carbocation's energy, making it much easier to form.
And can aromaticity itself help?
Absolutely. When the vacant p orbital is part of a fully conjugated cyclic system that satisfies Huckel's rule, like 4n plus 2 pi electrons, you can get significant stabilization through aromaticity. The classic example is the cyclopropanylium ion, a three-membered ring cation that's surprisingly stable due to having 2 pi electrons, making it aromatic.
And what about elements that possess lone pairs of electrons, like nitrogen or oxygen, attached to the carbocation carbon? How do they affect stability?
Oh, they are extremely effective stabilizers. Heteroatoms such as nitrogen, oxygen, and even halogens like fluorine, chlorine, bromine, iodine, anything with lone pairs can stabilize an adjacent carbocation.
How?
They do this through direct donation. They donate their lone pair electrons directly into the empty orbital of the carbocation. This forms a temporary partial pi bond, like CO plus or CM plus, and powerfully delocalizes the positive charge onto the heteroatom itself.
So the heteroatom takes some of the positive charge.
A significant amount, yes. Nitrogen and oxygen are particularly potent donors and thus excellent carbocation stabilizers. What's often surprising to students is that even halogens, despite being very electronegative and usually thought of as electron withdrawing through sigma bonds, inductive effect,
Right, they pull electrons.
they can still stabilize carbocations through this resonance effect, this donation. In fact, computationally, fluorine is actually more effective as a donor than a methyl group at delocalizing positive charge.
Fluorine, really? But it's so electronegative.
I know, it seems backwards. However, fluorine's very strong polar effect, its powerful electronegativity, pulling electron density away through the sigma bond, works in the opposite direction. So its net stabilization effect might be less than that of powerful resonance donors like nitrogen or oxygen, or maybe even less than alkyl groups, depending on the system, because the inductive withdrawal fights against the resonance donation. It's a balance.
That's a bit counterintuitive for halogens. Okay, so where does the positive charge actually reside in these stabilized carbocations? Does it stay mostly on the carbon, or does it really shift onto the substituent?
That's an excellent question, and computational chemistry gives us really good insights here, using things like natural population analysis, NPA charges.
Okay.
For most substituents, like alkyl groups, the positive charge remains largely localized on the original cationic carbon. Hyperconjugation spreads it a bit, but the carbon bears most of it. However, for strong donors like nitrogen or oxygen, the positive charge delocalizes significantly onto the substituent itself, onto the N or O atom. This beautifully reflects the strong resonance contribution where you draw the double bond and the positive charge on the heteroatom.
Makes sense.
What's particularly interesting, and maybe counterintuitive again, is that calculations suggest more substituted alkyl carbocations, like the tertiary butyl or the 2-propagations, isopropyl, actually have a greater positive charge calculated on the central trigonal carbon than simpler ones like ethyl.
More substituted means more charge on the center. How?
It seems odd, but it's consistent with experimental NMR data. The source suggests that in tertiary rotations, the stabilization might come from a complex pattern of alternating positive and negative charges throughout the framework, with the hydrogens actually bearing a significant portion of the overall positive charge due to hyperconjugation and induction. It's not just about the central carbon.
Negative charges, subtler effects.
Let's flip the charge now. What about Carbanion species with a negative charge and a lone pair on carbon? How are they structured, and what influences their stability, especially since they're often highly reactive bases in nucleophiles?
Carbanions are the flip side, yes. Structurally, they typically adopt a pyramidal geometry around the negatively charged carbon.
Pyramidal, like ammonia.
Exactly like ammonia. The carbon atom is usually considered sp3 hybridized, and the lone pair of electrons occupies one of the sp3 orbitals. The reason for this pyramidal shape, rather than flat trigonal planar-like carbocations, is that the lone pair is more stable lower in energy when it resides in an orbital with some s character. Sp3 orbitals have 25% s character, which helps stabilize the negative charge compared to putting it in a pure p orbital.
Okay, sp3 and pyramidal. How are they stabilized electronically?
They are stabilized by any group that can effectively disperse or withdraw the negative charge from the carbon center, preventing it from being too concentrated and reactive. Electron withdrawing groups are good for carbanions.
So how do alkyl groups, which were so good at stabilizing carbocations by donating electrons, affect carbanions? Do they stabilize them too?
Generally, no. In fact, simple alkyl groups are often slightly destabilizing for carbanions because of their mild electron-donating inductive effect, which pushes more negative charge onto an already negative center.
So the opposite effect of carbocations.
Pretty much the opposite inductive effect, yeah. And the magnitude is much smaller. The difference in stability between, say, a primary and a tertiary carbanion is only about 10 kilocalories per mole, a stark contrast to the roughly 75 kilocalmol difference seen for carbocations.
Much less sensitive to alkyl groups.
Much less. Interestingly, though, while smaller alkyl groups might slightly destabilize, larger alkyl groups can contribute some stabilization through polarizability.
Polarizability, how does that help?
Their larger, more diffuse electron clouds can distort and deform to help spread out the negative charge over a larger volume. It's like having a bigger cushion to absorb the charge. So polarizability helps stabilize anions in general.
What are the most effective stabilizing groups for carbanions then, if not alkyl groups?
The most effective are groups that can withdraw electrons through the electron acceptors.
Like what?
Think nitro, NO2, cyano-CN, and carbonyls groups, like in esters or ketones. These provide strong stabilization by delocalizing the negative charge from the carbon into the electron-withdrawing pi system of the substituent. You can draw resonance structures showing the negative charge moving onto the oxygen or nitrogen atoms.
Okay, resonance withdrawal is key. What else?
Additionally, elements from the third and fourth rows of the periodic table, like sulfur, think sulfones, phosphorus, phosphonium, halides, and silicon, also stabilize adjacent carbanions. This is sometimes attributed to their ability to accommodate charge via available d orbitals, although polarization is also certainly important.
And halogens?
For halogens, the order of stabilization is FClBr. Fluorine is actually slightly destabilizing compared to hydrogen, while chlorine and bromine are stabilizing.
That's the opposite of their electronegativity order.
It is. This suggests that polarization effects, the ability of the electron cloud to distort, are more important than simple inductive effects, electronegativity, for halogen stabilization of carbanions. The larger electron clouds of Cl and Br can accommodate the negative charge better.
This directly leads us to understanding hydrocarbon acidity, doesn't it? The easier it is to form the carbanion, the more acidic the hydrocarbon.
It absolutely does. The stability of the carbanion formed by deprotonation, removing H+, directly correlates with the acidity, measured by pKa, of the hydrocarbon from which it was formed.
And how does structure affect acidity?
We see a sharp increase in acidity based on the hybridization of the carbon bearing the acidic hydrogen. sp3CH bonds, like in alkanes, are the least acidic. Highest pKa, maybe 50-60. sp2CH bonds, like in alkenes or benzene, are more acidic, pKi around 40-45. And sp-CH bonds, in terminal alkanes, are the most acidic among simple hydrocarbons, pKa around 25.
Why the big jump with hybridization?
It's all about the cis character of the orbital holding the lone pair in the carbanion. Sp orbitals have 50% stickshare, sp2 have 33%, and sp3 have 25%. Electrons in orbitals with more cis are held closer to the positively charged nucleus, which stabilizes the negative charge more effectively.
Closer to the nucleus is better for negative charge.
Exactly. That's why terminal alkynes with their sp hybridized carbons are significantly more acidic than other hydrocarbons. For example, phenylacetylene has a pK near 26.5, making it acidic enough to be readily deprotonated by strong bases like sodium amide in the lab.
And what's considered the most dramatic example of carbanion stability leading to high acidity?
That would have to be cyclopentadiene. It's truly exceptional.
Cyclopentadiene, the five-membered ring with two double bonds.
Right. Its acidity is astonishing for a hydrocarbon, with a pK similar to common alcohols, around 16.
pKi 16, why so acidic?
Its exceptional acidity stems entirely from the aromaticity of the resulting cyclopentadienyl anion. When you remove a proton, the resulting carbanion has 6 pi electrons delocalized in a cyclic planar system. It perfectly fits the criteria for aromaticity. This aromatic stabilization makes the anion incredibly stable, thus making the parent hydrocarbon remarkably acidic.
So aromaticity trumps everything else here.
It's a huge stabilizing factor, yes. The source even mentions computational predictions that some exotic, highly strained molecules like tetrahedrine might be comparable to water in acidity, which is mind-boggling, and hints at the hidden acidities chemists are still uncovering in unexpected structures.
How did chemists determine these hydrocarbon acidities in practice, especially for the really weak acids where the carbanion concentrations might be vanishingly tiny?
There are several sophisticated methods, as direct measurement is often impossible. For somewhat stronger carbon acids, spectroscopic measurements can be used, often by comparing the anion concentration to a series of known indicators to establish a basicity constant H scale. For very weak acids, where carbanion concentrations are too low to measure directly, even with indicators, kinetic measurements are often the way to go.
Measuring rates again.
Yeah. This often involves isotopic exchange rates. For instance, you see how quickly hydrogens in the molecule are replaced by deuterium or tritium from a labeled solvent or catalyst. The rate of this exchange correlates directly with the ease of carbanion formation and thus the acidity.
Clever.
And for extremely unreactive saturated hydrocarbons, where even exchange is too slow, specialized electrochemical methods are sometimes employed. These might involve measuring the reduction potential needed to turn the hydrocarbon radical into the carbanion, which can then be related back to the acidity.
The odd electron out.
Now, for radicals, those fascinating neutral species with an unpaired electron, do they show significant electronic substituent effects despite not having a net charge? I might guess that with no formal charge, the effects would be minimal compared to ions.
That's a common misconception, actually. They absolutely show significant electronic effects, sometimes quite powerfully.
Really? Even though they're neutral?
Yes. Radicals also follow the same general stability order based on alkyl substitution as carbocations. Tertiary, secondary, primary. Okay. A tertiary radical is more stable than a secondary, which is more stable than a primary.
Okay, same trend as carbocations there.
And this trend is consistently observed experimentally, for example, in hydrogen atom abstraction reactions. How easily you can pull off a hydrogen atom with another radical depends on the stability of the carbon radical you leave behind.
Makes sense.
And just like carbocations, allylic and benzylic hydrogens are notably more reactive towards radical abstraction, maybe 9 times more reactive toward methyl radicals than typical CH bonds.
Why?
Because removing them forms the highly stabilized allylic or benzylic radicals. This enhanced reactivity is a direct indicator of a more stable radical intermediate being formed.
How are radicals stabilized electronically if there's no formal charge to delocalize in the same way as ions? What stabilizes that lone electron?
Primarily through resonance and hyperconjugation, much like carbocations,
Right.
but the details are a bit different. Resonance is huge. Groups like vinyl in allylic radicals and phenyl in benzyl radicals provide substantial stabilization by allowing the unpaired electron to be delocalized, spread out over their extended pi systems. You can draw resonance structures showing the dot moving around.
Right, moving the radical electron.
This effectively spreads out the oddness of that unpaired electron, lowering its energy. And we can quantify this stabilization by observing a significant lowering of the CH bond dissociation energy, BDE, for the bond that needs to break to form the radical. For example, forming the allylic radical from propene requires about 13.4 kilocalories per mole, less energy than breaking a typical CH bond in propane. That's the stabilization energy.
That's significant. And what about other common functional groups attached to the radical center? Do they generally stabilize or destabilize radicals?
This is where it gets really interesting and maybe counterintuitive again. Nearly all common functional groups, whether they are generally considered electron withdrawing groups, EWGs like carbonyl CO and cyano, or electron releasing groups, ERGs like methoxy, omebo, and dimethylamino, actually have a net stabilizing effect on an adjacent radical center.
Wait, both withdrawing and releasing groups stabilize a radical? How does that work? That seems contradictory.
It does seem odd, but it comes down to the specific orbital interactions involved with that singly occupied molecular orbital, the HOMO, holding the unpaired electron.
Okay, orbital interactions.
For unsaturated electron withdrawing groups like a carbonyl, the radical's half-filled porbital, the HOMO, interacts favorably with both the filled pi orbitals and the empty pi star orbitals of the substituent. These interactions effectively lower the energy of the HOMO, stabilizing the radical. This interaction also tends to make the radical itself more electrophilic, more eager to accept an electron.
Okay, EWGs stabilize and make it electrophilic. What about donors?
For electron donors substituents with lone pairs, like an amine or ether, the strongest interaction is between the unpaired electron in the radical's porbital and a non-bonding electron pair on the donor atom, like the nitrogen or oxygen lone pair. This interaction actually raises the energy of the HOMO slightly, but it significantly lowers the energy of the donor's lone pair. The net effect is stabilizing overall.
So stabilizing the donor's electrons stabilizes the radical overall?
Yes, the overall energy of the system is lowered. And in this case, the interaction tends to make the radical center more nucleophilic, more willing to donate its electron. You can also depict these interactions using resonance structures. For EWGs, you might show the radical electron moving into the pi system. For donors, you can draw a structure with a double bond and the radical electron formally on the donor atom, or even dipolar structures.
So we have quantitative measures of stability for ions, like carbocations and carbanions. Do we have something similar for radicals, like a table of stabilization energies?
Yes, we do. Chemists calculate or estimate radical stabilization energies, RSEs. These values are often derived by comparing experimental atomization enthalpies to sums of standard bond energies, similar to how Benson's method works, to quantify the extra stability beyond simple additivity.
And do these RSE values match chemical intuition?
Generally, yes. They provide quantitative values that are mostly consistent with chemical experience. For example, they clearly show the high stability of benzyl and ally radicals compared to simple alkyl radicals. However, you have to interpret them carefully sometimes.
How so?
For some radicals that appear destabilized in these tables, like the trichloروmethyl radical, CCl3, or the acetyl radical, CH3CO, their apparent low stability, meaning a high RSE value, might be partly due to similar destabilization effects already present in their stable reactant precursors, like CCl4 or acetaldehyde. So the net effect on the activation energy of a reaction forming these radicals might not be as unfavorable as the raw RSE value alone might initially suggest. You have to consider the starting point, too. 3.5 carbonyl addition intermediates. Reactivity dictated by X.
Let's turn our attention now to carbonyl compounds, aldehydes, ketones, esters, amides, and so on. They are absolutely central to so many organic reactions. How do the different substituents attached directly to the carbonyl group influence their reactivity, especially when reacting with nucleophiles?
The reactivity of carbonyl compounds towards nucleophiles varies enormously based on that substituent, often just denoted as X in RCOX. This reactivity trend is one of the most fundamental organizing principles in organic chemistry.
What is the general trend?
For nucleophilic addition at the carbonyl carbon, which is a critical first step in many reactions, the order of increasing reactivity is generally carboxamide, XnR2, is least reactive, then ester XOR, then ketone XR, then aldehyde SH, and finally acyl halides like acyl fluoride XF or chloride are most reactive.
Amide, ester, ketone aldehyde, acyl halide. Okay. What accounts for such a distinct and consistent trend across this wide range of common functional groups?
Two main electronic effects from that substituent X attached to the carbonyl carbon are at play, and they often work together to establish this trend.
Okay, what are they?
First, there's the polar effect, mainly inductive withdrawal. A more electronegative substituent X pulls electron density away from the carbonyl carbon through the sigma bond. This makes the carbonyl carbon more electron deficient, more positive, more electrophilic.
More attractive to nucleophiles?
Exactly. It increases its reactivity towards incoming electron-rich nucleophiles. Second, there's resonance electron donation. If substituent X has unshared electron pairs readily available, like the nitrogen and amides or the oxygen and esters, it can donate these electrons into the carbonyl pi system through resonance. You can draw a resonance structure with a double bond between C and X and a negative charge on the carbonyl oxygen.
Right, CX plus O.
Something like that. This resonance effect does two things. It stabilizes the carbonyl compound itself, making it less eager to react, and it simultaneously reduces the electrophilicity of the carbonyl carbon by pumping electron density back towards it. So resonance donation decreases reactivity towards nucleophiles.
So these two effects, polar withdrawal and resonance donation, can either reinforce each other or oppose each other, depending on the group X.
They often reinforce the observed trend, leading to that clear order of reactivity we mentioned. Let's look at the extremes.
Okay.
Consider the amido group in carboxymides. Nitrogen is the strongest resonance donor among these common groups. It's less electronegative than oxygen, so its lone pairs are more available, but it's also the weakest polar acceptor, inductive withdrawer. This combination, strong donation, weak withdrawal, leads to very low reactivity for amides. They're quite stable carbonyls.
Makes sense. What about the other end, acyl fluorides?
Conversely, fluorine in an acyl fluoride is the weakest donor. Its lone pairs are held very tightly by the highly electronegative F atom, but it's the strongest acceptor through its extreme electronegativity, strongest inductive withdrawal. This combination, weak donation, strong withdrawal, makes acyl fluorides exceptionally reactive towards nucleophiles.
Okay, the balance determines the reactivity.
Precisely. And computational analyses, like looking at calculated CX pi bond orders or charge distributions, can quantify the extent of this resonance delocalization and beautifully confirm its crucial influence on the observed reactivity trend.
Now, this section in the source brings up a really fascinating and maybe counterintuitive point related to the hydrolysis of methyl acetate in water. It mentions that calculations in the gas phase show a very small barrier for hydroxide adding to the ester, but in solution, the measured barrier is surprisingly large. How can the environment, the solvent, change things so dramatically?
This is a powerful demonstration of the often underestimated impact of solvation effects. It's a classic example. While gas phase calculations, modeling just the ester and hydroxide ion in isolation, indeed predict a very small activation barrier for the hydroxide addition step.
Like it should be easy.
Right. The dominant factor contributing to the observed large activation barrier in solution, around 18.5 kilocalories per mole for the actual hydrolysis, is the energy cost of desolvating the hydroxide ion before it can attack.
Dissolvating. You mean stripping off the water molecules?
Exactly. The hydroxide ion is very strongly solvated in water, forming numerous strong hydrogen bonds with surrounding water molecules. These interactions are very stabilizing for the hydroxide ion.
Okay.
To react with the relatively non-polar ester carbonyl, the hydroxide ion must shed some of these highly stabilizing solvent molecules. It has to break those favorable hydrogen bonds. This desolvation process costs a significant amount of energy.
And that energy cost adds to the barrier.
It becomes the major part of the activation barrier in solution. This underscores the immense importance of solvation effects, particularly for charged species like hydroxide. It shows how they can be the primary determinants of reaction rates, sometimes completely overshadowing the intrinsic molecular reactivity you might predict just by looking at the molecules in a vacuum. The solvent isn't just a passive medium, it's an active participant.
How does this understanding of carbonyl reactivity, considering both electronic effects and these solvation effects, translate into practical applications in organic synthesis? How do chemists use this knowledge?
Knowing these polar and resonance effects and how solvents might play a role is absolutely vital for designing specific transformations in the lab. You choose your carbonyl derivative based on the reactivity you need.
Like using acyl chlorides for high reactivity.
Exactly. Acyl chlorides, or CS fluorides, are highly reactive for nucleophilic acyl substitution reactions, precisely because the halogen's strong electron withdrawing nature and relatively weak donation make them excellent leaving groups and activate the carbonyl. This makes them ideal starting materials for making esters or amides, reactions that might be difficult starting from a less reactive carbonyl.
And the opposite end?
In stark contrast, trying to do nucleophilic substitution on a carboxylate anion, RCOO, is nearly impossible under normal conditions.
Why is that?
2 reasons. First, there's a very high activation energy for the initial nucleophilic addition step, because the negatively charged carboxylate strongly repels the incoming negatively charged nucleophile, like charges repel. Second, even if an intermediate tetrahedral species somehow formed, the O2 group would be an incredibly poor leaving group. It's just not going to leave.
Reactivity really spans a huge range.
It does. And if you think about the substituent X changing across the periodic table, say from fluorine in RCOF to oxygen in RCF to nitrogen in RCnR2 to carbon in RCOCH3, or even a negatively charged carbon, like in an enolate. The increasing electron donation from that substituent X fundamentally transforms the carbonyl group itself. It shifts from being a strong electrophile in acylhalizides, eager for electrons, to being part of a nucleophilic structure in anionic derivatives like enolates, which are electron-rich and attack electrophiles. This fundamental shift dictates how these compounds behave in a vast array of reactions, offering chemists incredibly powerful handles to control their synthetic strategies.
Advanced tools and environmental influences. 4.1 Kinetic isotope effects, Ki. Peaking at the rate-determining step.
We've covered a lot about how structure influences stability and reactivity through electronic effects. But how do chemists get even more detailed insight? Like, how can they tell exactly which bonds are breaking or forming during the slowest rate-determining step of a reaction? It seems impossible to actually see that moment.
That's where a really elegant technique comes in, kinetic isotope effects, or KIs. This is a specialized and incredibly powerful type of substituent effect, but instead of changing the element, you just change the isotope.
Isotopes, like deuterium instead of hydrogen.
Exactly. Most commonly, it involves replacing hydrogen, protium, H, with its heavier, stable isotope, deuterium D, or sometimes the radioactive isotope tritium T. The genius of it is that isotopes of the same element have virtually identical chemical properties. They react in fundamentally the same way electronically, but their masses are different.
Okay, tiny mass difference. Why does that impact the reaction rate? How can you tell anything from that?
It impacts the rate because of subtle differences in their quantum mechanical zero-point energy.
Zero-point energy.
Yeah. Every chemical bond vibrates constantly, even at absolute zero temperature. It can't be perfectly still. This minimum vibrational energy is its zero-point energy. Now, because deuterium is heavier than hydrogen, a CD bond vibrates at a slightly lower frequency than a CH bond.
Heavier means slower vibration.
Essentially, yes. And a lower frequency means a lower zero-point energy. The CD bond sits slightly lower down in its potential energy, well, compared to the CH bond.
Okay, CD starts lower. So what?
So if that specific bond, the CH or CD bond, is directly breaking or significantly changing its bonding in the rate-determining step of the reaction,
The slow step again.
then the deuterated molecule effectively faces a slightly higher activation energy to reach the transition state. This is because the energy difference between the transition state and the starting CD bond with its lower zero-point energy is greater than the energy difference for the CH bond.
It's a bigger hill to climb from the lower starting point.
Precisely. This results in a slower reaction rate for the deuterated species. We measure this as the ratio KH/KD, the rate constant for the hydrogen compound divided by the rate constant for the deuterium compound. If this ratio is significantly greater than 1, often in the range of 2 to 7 for CH bond breaking, we call it a primary Ki, and it's strong evidence that the CH bond is breaking in the rate-determining step.
Wow, that's clever. What about secondary KIs? These sound even more subtle if the bond with the isotope isn't directly breaking?
They are indeed more subtle, but they provide different kinds of information. Secondary KIs occur when the isotopically substituted atom, again usually HVSD, is not directly involved in the bond breaking or formation in the rate-determining step, but is often attached to the reacting center or nearby.
Okay.
These effects are typically much smaller than primary KIs, usually with KH/KD values in the range maybe 0.7 to 1.5. And notice they can be normal, KH/KD1, or inverse, KH/KD1.
Inverse. Faster with deuterium.
Sometimes, yes. What secondary KIs reveal are very subtle structural changes at the transition state, particularly changes in hybridization or coordination.
Like what?
For instance, if an sp3 hybridized carbon with CH bonds changes to sp2 hybridization, like forming a carbocation or a double bond, at the transition state, the CH bending vibrations become less restricted, easier. This usually leads to a normal secondary Ki, KH/KD slightly 1. Conversely, if coordination at the reaction center increases in the transition state, maybe making things more crowded and restricting CH vibrations, you might see an inverse secondary Ki, KH/KD1. They're like a chemical stethoscope, listening for the most delicate vibrational changes during the reaction.
That's incredibly precise information from such tiny mass differences. Has there been any recent advancement in measuring Kis that makes them even more accessible or powerful for chemists?
Yes, there's been a remarkable advancement in recent years. The ability to determine Kis using compounds of natural isotopic abundance measured very precisely by NMR spectroscopy.
Natural abundance, you mean without making special deuterated molecules?
Exactly. Deuterium exists naturally at about 0.015% abundance, carbon-13 at about 1.1%. The method relies on the principle that as a reaction proceeds, the slightly slower reacting heavier isotope, like D or 13C, becomes fractionally enriched in the remaining unreacted starting material.
The slow ones get left behind.
Precisely. By measuring this very subtle enrichment using high-precision NMR, you can calculate the Ke. The beauty is that this allows for simultaneous analysis of isotope effects at multiple atomic positions within the same molecule, all in one experiment, without the often difficult and expensive synthesis of specifically labeled reactants. It's a huge leap forward for probing reaction mechanisms with incredible detail. 4.2 linear free energy relationships. LFER, quantifying substituent power.
We've seen lots of examples of how substituents affect things. This next topic sounds like a way to bring some quantitative order to that diverse and sometimes confusing world of substituent effects we've been discussing. Linear free energy relationships.
Exactly. Linear free energy relationships, or LFERs, provide a powerful quantitative framework for understanding and predicting how substituents affect reaction rates and equilibria across different reactions. The most widely known and truly foundational of these is the Hammett equation.
The Hammett equation. I've definitely heard of that one. How does it actually work? What does it tell us in practical terms?
It's based on a brilliant correlation. It relates the logarithm of a reaction's rate constant K, or equilibrium constant K, for a substituted aromatic compound, like a substituted benzoic acid or phenol, with a unique parameter for that substituent called the substituent constant.
Sigma.
Think of the SOLU as a numerical fingerprint for a substituent's overall electronic effect, whether it's electron donating or electron withdrawing, and how strongly. These values are derived from a standard reference reaction, which is typically the ionization of substituted benzoic acids in water. Electron withdrawing groups get positive values, electron donating groups get negative values.
Okay, tells you about the substituent. What else is in the equation?
The other key part is the slope you get when you plot the log of the rate equilibrium constant for your reaction versus the values for a series of substituents. This slope is called the reaction constant, rho.
Rho. What does rho tell you?
Rho is like a sensitivity meter for that specific reaction you're studying. It tells you how sensitive that particular reaction's rate or equilibrium is to the electronic influence of substituents attached to the aromatic ring.
So if that reaction constant is positive, what does that imply about the reaction mechanism or its transition state?
A positive value tells us that electron-withdrawing substituents, which have positive values, accelerate the reaction, increase log K. This typically happens when a negative charge develops or increases, or a positive charge is destabilized, in the transition state of the rate-determining step. Electron-withdrawing groups help stabilize that developing negative charge or handle the destabilized positive charge.
Okay. And negative rho.
Conversely, a negative rho implies that electron-releasing substituents with negative values accelerate the reaction. This usually happens when a positive charge develops or increases in the transition state, and electron-releasing groups are needed to stabilize it. The magnitude of rep tells you how much charge is developing. A large positive or negative means the reaction is very sensitive to substituents, suggesting significant charge development in the TS.
And the Hammett equation usually works for specific positions.
Yes, it's particularly elegant because it applies most directly to meta and para substituents on a benzene ring. This setup cleverly avoids the complicating factor of direct steric interactions between the substituent and the reaction site, allowing chemists to isolate and study purely electronic effects transmitted through the ring. Ortho substituents are often excluded because they can have additional steric or proximity effects.
Are there more complex versions of the Hammett equation? What if a substituent has a really strong resonance interaction directly with the reaction center, not just a general polar effect?
Yes, absolutely. The original Hammett's values work best when direct resonance between the substituent and the reaction center isn't dominant. For situations where it is dominant, like a paranitro group withdrawing electrons from a developing negative charge, or a paramethoxy group donating to a developing positive charge, more specialized substituent constants are used. These include S+ constants for substituents stabilizing positive charge via resonance, and SOC constants for substituents stabilizing negative charge via resonance.
Okay, plus and...
And even more advanced approaches exist, like the dual substituent parameter equation, using parameters like II for inductive field effects and SAR for resonance effects. These allow chemists to separately dissect the relative contributions of the polar effects and resonance effects of each substituent. This provides a much deeper and more nuanced understanding of exactly how each substituent is electronically influencing the reaction center.
What are the implications of the solvent on these LFERs? Does a Hammett plot say, look different if you run the reaction in water versus in the gas phase?
Crucially, yes. Substituent effects, as measured by these correlations, are generally much stronger in the gas phase compared to in solution.
Stronger in gas. Why?
Because in the gas phase, there's no solvent around to level or dampen the charge changes that occur in the reactant or transition state. The full electronic effect of the substituent is felt directly without any solvent molecules stepping in to stabilize charges. In solution, the solvent can solvate and stabilize developing charges, effectively making the electronic effects appear less dramatic, often leading to smaller values.
Interesting. Does solvent affect resonance versus polar effects differently?
It seems so. The relative importance of direct resonance interactions often appears to be greater in polar solvents like water compared to the gas phase. This might suggest that solvation can actually help facilitate charge separation, making those resonance structures with separated charges more accessible and important in solution.
And what if you make a Hammett plot log as versus, and it isn't linear? Does that mean the whole idea is flawed for that reaction?
Not at all. In fact, nonlinear Hammett plots are often highly significant and are incredibly valuable mechanistic clues. They don't mean the LFR concept failed. They usually mean something interesting is happening mechanistically.
Like what?
A break or curve in a Hammett plot can indicate a change in the reaction mechanism itself, or a shift in the rate determining step as the electronic nature of the substituents is varied across the series. For example, in the formation of semicarbozones from substituted benzaldehydes, the Hammett plot is famously V-shaped.
V-shaped?
Yes, it has different slopes, values, for electron-releasing versus electron-withdrawing groups. This nonlinearity strongly suggests that the rate-limiting step actually changes, maybe from nucleophilic attack to dehydration, depending on whether the substituent is donating or withdrawing electrons. These breaks in linearity provide invaluable insight into the dynamic nature of reaction pathways.
Guiding reactions to success.
Let's discuss catalysts. We often hear about these substances that accelerate reactions without actually being consumed in the process. What's their fundamental role in terms of energy, and how do they actually make reactions go faster?
Catalysts are essential tools in chemistry. Their fundamental function is to provide an alternative reaction pathway, a different route from reactants to products that has a lower overall activation energy, EEA or AG, compared to the uncatalyzed pathway.
Lowering the barrier again.
Exactly. They lower the height of that energy barrier, which means that at a given temperature, a larger fraction of molecules have enough energy to get over the barrier in a given time. This directly leads to a faster reaction rate.
But they don't change where the reaction ends up, right?
That's absolutely crucial.
Yeah.
Catalysts do not affect the equilibrium position of a reaction. They don't change the overall DG between reactants and products. They only change how quickly that equilibrium is reached. They don't make impossible reactions possible. They just make slow reactions faster.
And the most general type of catalysis, especially in organic chemistry in solution, often involves proton transfer. This is called Brunstad acid and base catalysis.
Yes, that's correct. It's incredibly common. Brunstad acid catalysis works by having an acid donate a proton to a reactant, typically making it more reactive.
How?
For example, protonating the oxygen of a carbonyl group makes its carbon significantly more electrophilic, more electron deficient, because the oxygen is now positively charged and pulling electrons harder. This makes the carbonyl much more susceptible to attack by weak nucleophiles.
Okay. And base catalysis?
Base catalysis, conversely, works when a base removes a proton from a reactant or a nucleophile. This often converts a neutral molecule into a much more reactive anion, like forming an enolate from a ketone, or makes a weak nucleophile, like water, into a much stronger one, like hydroxide.
What's the difference between general and specific catalysis? That distinction sometimes seems a bit tricky.
It can be, but it reveals important details about when the proton transfer happens relative to the slow step. Let's take acid catalysis. Specific acid catalysis means that only the solvated proton itself, which is H3O plus A, the hydronium ion in water, is responsible for the catalysis. The rate depends only on the pH.
Okay. When does that happen?
This usually occurs when there's a fast, reversible pre-equilibrium protonation of the reactant before the slow, rate-determining step. The proton just needs to be available. The actual active proton transfer isn't part of the slow step.
And general acid catalysis?
General acid catalysis, on the other hand, means that any Brunstad acid present in the solution, not just H3O+, can contribute to the observed rate. The rate depends on the concentration of each individual acid. This implies that the proton transfer step itself is involved in the rate-determining step. The proton is being transferred during the slow part of the reaction.
So specific means proton transfer is fast and before the slow step. General means it's part of the slow step.
That's a good summary, yes. And the same distinction applies to specific base catalysis, only OH matters, versus general base catalysis. Any base B can participate in the slow step. By carefully studying how the reaction rate changes with pH, or with the addition of different buffer components, different acids HA and their conjugate bases A, chemists can distinguish these possibilities and get crucial clues about the timing of proton transfer in the mechanism. Plotting reaction rate versus pH often reveals characteristic profiles for each type.
Can you give an example of this complexity, maybe something relatable whose breakdown depends on pH in a complicated way?
The hydrolysis of aspirin, acetylsalicylic acid, is a classic case study often used to illustrate this. Its pH rate profile, how fast it breaks down at different pH values, is much more intricate than that of a simple ester like methyl acetate. It shows additional upward and downward bends in the plot. These reveal extra mechanistic pathways, likely involving aspirin's own carboxylic acid group participating in the reaction, either acting as an internal catalyst or influencing reactivity once it becomes ionized at higher pH. Analyzing this complex profile helps chemists understand the multiple ways aspirin can degrade, which is important for formulation and stability.
What about catalysts that aren't just protons or hydroxide ions? Lewis acid catalysis is another huge area in organic synthesis, isn't it?
Indeed it is. Lewis acid catalysis involves species that act as electron pair acceptors rather than proton donors. Brunstad acids.
Electron pair acceptors, like metal ions.
Often, yes. These can be metal cations like lithium Li+, magnesium Mg2+, zinc Zn2+, or many transition metals. Or they can be neutral compounds that have an electron-deficient atom with an empty orbital, like boron trifluoride Bf3 or aluminum chloride LCl3.
How do these Lewis acids actually boost reactivity? What are they doing?
They typically boost reactivity by coordinating to lone pairs on donor atoms within the reactant molecule, often an oxygen or nitrogen.
Sticking to the lone pairs.
Yeah. This coordination pulls electron density away from the rest of the molecule, increasing the effective electrophilicity of the nearby reaction center. For example, if a Lewis acid coordinates to the oxygen of a carbonyl group, it makes the carbonyl carbon even more electron deficient, and thus much more reactive towards nucleophilic attack. This allows reactions to happen with weaker nucleophiles or under milder conditions than would otherwise be possible.
So they activate the electrophile.
Exactly. Another key example is in Diels-Alder reactions. Lewis acids are often used to accelerate these cycle additions. They coordinate to the dienophile, often an electron-deficient alkene or carbonyl compound, lowering the energy of its LUMO stellar, lowest unoccupied molecular orbital,
lower LUMO,
which enhances its interaction with the diene's HOMO, highest occupied molecular orbital, leading to a lower activation energy and a much faster reaction.
Is there a way to predict which Lewis acids work best with which molecules?
Qualitatively, the hard-soft acid-base HSAB concept can be useful. It suggests that hard Lewis acids, small, highly charged, not easily polarizable like La+ or Al3+, prefer to coordinate with hard Lewis bases like oxygen or fluorine atoms, while soft Lewis acids, larger, lower charge, more polarizable like Ag+ or Hg2+, prefer soft Lewis bases like sulfur or iodine atoms. Matching hardness helps predict stronger complexation.
Hard likes hard, soft likes soft.
Generally, yeah. You could also empirically measure Lewis acid strength experimentally, for instance, by observing their effect on the NMR chemical shifts of standard indicator molecules, like acetone or crotonaldehyde. How much the signal shifts upon complexation gives a quantitative ranking of Lewis acidity, 4.4 solvent effects, the hidden hand of the environment.
Finally, let's talk about the profound influence of the solvent on reactions. It often feels like the unsung hero or sometimes the villain, controlling things behind the scenes in a chemical process.
You're absolutely right. Solvent effects can be enormous, impacting both reaction rates and equilibrium positions profoundly, sometimes changing rates by factors of millions or even billions.
Wow. How do chemists categorize solvent effects?
We typically distinguish between macroscopic properties of the solvent, bulk properties, like its dielectric constant, which is a measure of its ability to insulate charges from each other, and its molecular dipole moment, which reflects the polarity of individual solvent molecules.
Okay, bulk polarity.
And then more subtle, specific interactions at the molecular level. The most important of these is hydrogen bonding.
How do these bulk solvent properties, like dielectric constant, relate to reactivity?
There are some general guidelines based on how charge changes during the reaction. A high dielectric constant, like water in 80, indicates a solvent's strong ability to accommodate and stabilize separated charges. Therefore, reactions that involve significant charge separation in the transition state compared to the reactants.
Like SN1 reactions forming ions.
Exactly, like SN1 reactions, where a neutral molecule forms a carbocation and an anion in the transition state. These reactions are dramatically favored and accelerated by highly polar solvents with high dielectric constants. These solvents effectively surround and stabilize the developing charges in the transition state, lowering its energy. Okay, polar solvents good for charge separation. What about the opposite?
Conversely, reactions where species of opposite charges combine, leading to a less charged transition state, charge destruction.
Ions coming together.
Right. These reactions are often favored by less polar solvents. This is because the polar solvents would strongly stabilize the initial charged reactants, making them lower in energy and less reactive, a higher barrier to reaction. In less polar solvents, the initial charged reactants are less stabilized, higher in energy, and thus more eager to react to form the less charged transition state.
So the solvent's ability to stabilize charges is key. Absolutely. And this can lead to those massive rate differences we mentioned. Chemists have developed empirical scales to quantify this. For example, the Winstein Y values quantify a solvent's overall ionizing power based on the solvolysis rate of a standard compound, T-butyl chloride.
What do they show?
They show huge differences. For example, the solvolysis of T-butyl chloride shows a rate difference of more than 106, a millionfold, just between water, Y equals plus 3.49, very ionizing, and T-butyl alcohol, Y equals a meter to 3.2, much less ionizing. It powerfully demonstrates just how critical solvent choice is in controlling reaction rates, especially for reactions involving ions.
So those are the general bulk solvent effects based on polarity. What about the specific solvent interactions, like hydrogen bonding? How do they influence reactivity?
These specific interactions are incredibly important, especially the distinction between product and erotic solvents.
Product means it has an H on an O or N.
Exactly. Product solvents like water, alcohols, methanol, ethanol, or carboxylic acids are very good at forming hydrogen bonds, acting as H-bond donors. They can heavily hydrogen bond to and stabilize anions, negatively charged ions. This strong solvation effectively lowers the anion's energy, surrounds it with solvent molecules, and makes it less reactive as a nucleophile or base.
Okay, protic solvents cage up anions. What about a protic?
Polar protic solvents, on the other hand, think DMSO, dimethyl sulfoxide, DMF, dimethylformamide, acetonitrile are polar. They have dipole moments and moderate dielectric constants. But they cannot act as hydrogen bond donors because they lack that acidic H on an O or N.
Right.
While they can solvate patients well, they cannot effectively hydrogen bond to anions. This leaves the anions much less solvated, essentially naked in the solution.
Naked anions.
Yeah, that's the term often used.
Yeah.
These naked anions are at a much higher energy level and are therefore much, much more reactive as nucleophiles or bases compared to when they're in a protic solvent. They're not bogged down by a tight solvent shell.
And this difference between proprotic and polar protic solvents, especially for anion reactivity, then opens the door for powerful synthetic strategies like using crown ethers or phase transfer catalysis, doesn't it?
Exactly. That's where these ideas become really practical synthetically. Crown ethers are fascinating macrocyclic polyethers, ring-shaped molecules with multiple oxygen atoms. They're designed to specifically bind and encapsulate certain medications, like sodium Na+ or potassium K+, fitting them snugly inside their cavity.
Like a crown for the ion.
Precisely. When you add a crown ether to a nonpolar solvent, it can dramatically increase the solubility of an ionic salt, like KF or KCN, that would normally be insoluble. The crown ether wraps it up the anion, making the whole complex soluble in the organic solvent. And to maintain charge neutrality, the anion, like F or CN, is dragged along into the organic phase too.
So you get the anion into the nonpolar solvent.
Yes, and because the cation is shielded inside the crown ether, and the nonpolar solvent can't solvate the anion well, the anion is left highly reactive, a truly naked anion ready to attack organic substrates. It makes reactions like nucleophilic substitution with fluoride possible under mild conditions.
And phase transfer catalysis, similar idea.
Similar outcome, different mechanism. Phase transfer catalysts are typically salts with large, bulky, nonpolar cations, like tetranobutylammonium, B4N+. These cations are soluble in organic solvents. If you have a reaction system with an aqueous phase containing the nucleophilic anion, say hydroxide or cyanide, and an organic phase containing the substrate.
Two separate layers.
Right. The phase transfer catalyst can pick up an anion from the aqueous phase, ferry it across the phase boundary into the organic phase where the substrate is, allow the reaction to happen, and then potentially cycle back to pick up another anion. It effectively transfers the reactive anion into the phase where it's needed, enabling reactions between phases under exceptionally mild conditions.
A very practical example of this precise control using solvents and criterions is managing the outcome of alkylating ambident enolate anions. You mentioned enolates earlier. How do solvents play a role there, determining whether the oxygen or the carbon atom attacks the alkylating agent?
Enolate anions are classic ambident nucleophiles. They have two potential nucleophilic sites, the negatively charged carbon, constant carbon, and the oxygen atom. They can react at either site when treated with an electrophile like an alkyl halide.
C alkylation versus O alkylation.
Exactly. And the solvent in the criterion, like Li plus air, Neb plus air, or K plus, profoundly influence which site is favored. O-alkylation, reaction at oxygen, is generally favored when the enolate is least encumbered, meaning less solvated and less associated with its criterion, more like a free enolate. These conditions are often achieved using a polar protic solvent like DMSO or HMPA, maybe with a potassium criterion, which associates less tightly than lithium. Using a reactive alkylating agent like an alkyl sulfate also tends to favor O-alkylation.
Okay, less association favors O. What favors C?
C-alkylation, reaction at the carbon, usually the desired outcome for making CC bonds, is maximized under conditions where the enolate is more solvated or undergoes more significant ion pairing or even aggregation. This often happens when using an alkyl halide, less reactive than sulfate, in a less polar solvent like THF, or even a protic solvent. Using a tightly associating criterion like lithium also promotes C-alkylation.
So you can totally switch the outcome.
You can dramatically shift the balance. Even adding crown ethers can shift the balance towards O-alkylation by selectively solvating the metal criterion and freeing up the oxygen atom. This is a prime example of chemists precisely controlling reactivity and product selectivity through the subtle yet incredibly powerful manipulation of the reaction environment, solvent, criterion, temperature, additives. It's all part of the toolkit.
Wow, what an incredible journey through the world of structural effects on stability and reactivity. We've really seen how these fundamental principles, laid out so clearly in texts like Advanced Organic Chemistry, underpin pretty much everything, from just predicting whether a reaction is even feasible on paper to dictating the specific product you actually get in the flask.
It's true. By understanding these core concepts, free energy, activation barriers, the really nuanced roles of electronic substituent effects, KIEs, and then the powerful influence of catalysis and solvation, you gain a truly deep insight into how molecules actually behave and react at the most fundamental level.
It's truly fascinating to see how chemists use this whole array of tools from, simple calculations of bond energies or using Benson's rules, right up to sophisticated computational mapping of transition states or interpreting complex kinetic data like Hammett plots to not just observe, but to actively predict, explain, and ultimately control the molecular world around us.
It really is like having an instruction manual, or at least a very detailed guidebook, for the universe's tiniest machines.
And this knowledge isn't just, theoretical or academic, is it?
Not at all. It's directly applicable every single day in labs around the world for designing sophisticated new synthetic routes to make medicines or materials, for analyzing complex chemical systems in biology or the environment, and truly for engineering molecules with a specific purpose in mind.
So what does this all mean for you, our listener? Well, the next time you encounter a chemical reaction, maybe it's just baking soda and vinegar fizzing, or maybe something much more complex you read about. Remember that beneath the surface, it's this incredibly dynamic interplay of energies and structures. Molecules are constantly striving for stability, dictated by these paths of least resistance, the kinetics, and often profoundly influenced by the subtlest changes in their substituents or their surrounding environment.
Absolutely. Keep exploring, keep questioning. This deep dive, as detailed as we tried to be, has really only scratched the surface of the incredible complexity and, frankly, the beauty of organic chemistry. The more you look, the more connections you see, and the more surprises you'll find. It's a field that keeps on giving.
Couldn't agree more. Thank you so much for joining us on this deep dive into the heart of organic chemistry. We hope you found these insights valuable and that they spark even more curiosity. We'll be back soon with another exploration for our last-minute lecture family.